welcome to lecture series on advanced linear algebra. Friends, we have already learned the meaning of inner product in a vector space, and we have seen how an inner products give the concept of length of a vector in terms of norm of a vector please. We have also seen using the norm some important results related to inner product also we have seen, like first is the polarization identity, that is inner product of any two vector alpha beta. If we consider any two vector in a vector space V, the inner product of alpha beta is equal to, we have seen this is equal to 1 by 4 times sigma n equal to 1 to 4 I to the power n and norm of alpha plus I to the power n beta square. This is called polarization identity. And we have also seen that when norm is induced through this inner product, then norm of alpha plus beta the whole square plus norm of alpha minus beta whole square equal to 2 times of norm of alpha square plus 2 times of beta square. This is called the parallelogram law. See, here norm is induced through the inner product and it satisfied parallelogram law, and also the inner product of two vectors satisfies such type of polarization identity. This parallelogram law will tell you later on when you are studying the mathematical analysis, when you see the norm can be introduced by different ways, not through only inner products, then this parallelogram law will see that only satisfied when the norm is induced through inner product only. Another interesting thing we have also seen that when for a finite dimensional vector space V for a given order basis B, the inner product this can be expressed by an invertible Hermitian matrix which is also positive definite please. Now, we shall utilize this concept of inner product and see the combined impact of vector space and inner product. For that, what we will do? I will first introduce the concept of inner product space. So, let me define inner product space. Inner product space please. So, what is inner product space? A real or complex vector space along with an inner product in it is called as inner product space. So, now onwards I will use IPS please. Specifically, a finite dimensional real inner product space is called as Euclidean space. Euclidean space. Whereas a complex inner product space is called as unitary space. So, a vector space equipped with an inner product may be called as Euclidean space or inner product space depending on the if the vector space is finite dimensional and real, it is called the Euclidean space. If it is complex, then it is called the unitary space. So, note that this unitary space, the dimension of this vector space may be finite, may be infinite also. So, when you consider a vector space along with the inner product and we are saying that inner product space, definitely we can have also norm of every vectors and interesting results inner product space can be seen please. So, this interesting results let me express in terms of theorem please. Let V be an inner product space. So, it may be real, it may be complex please. For any alpha beta belongs to V and C belongs to the corresponding field, it may be real number, it may be complex number, then following properties holds good. Norm of C alpha equal to mod of C into norm of alpha. Second, norm of alpha is strictly greater than 0 for alpha not equal to 0. Third, magnitude of inner product of alpha beta is less than or equal to norm of alpha into norm of beta. This is called as Cauchy-Schwarz inequality. Cauchy-Schwarz inequality. Fourth one, norm of alpha plus beta is less than or equal to norm of alpha plus norm of beta please. This is called the triangular inequality. Okay. So, inner product space V following 4 axioms of property holds good. See, one, so let me prove one by one. The first one we have norm of C alpha square which is equal to inner product of C alpha C alpha. So, this is equal to C into C bar into alpha alpha. This is equal to mod C whole square into norm of alpha square. So, this implies norm of C alpha which is a positive quantity should be mod of C into mod of alpha. And second one is satisfying, since inner product of alpha alpha is strictly greater than 0 for alpha not equal to 0 implies norm of alpha square is strictly greater than 0. So, this implies norm of alpha is strictly greater than 0 for alpha not equal to 0. Third one, that is Cauchy-Schwarz inequality. For this we have to show magnitude of inner product of alpha beta is less than or equal to norm of alpha into norm of beta. See, if alpha equal to 0 or beta equal to 0, then this inequality is definitely satisfied. So, let alpha not equal to 0 and beta not equal to 0. So, for this case we have, let me consider gamma is another vector which is equal to beta minus inner product of beta and alpha divided by alpha square into alpha. You may raise the question, how to think that I have to consider gamma equal to like this. I will answer this question in my next in coming soon, basically when we are talking about this another terminology that is called orthogonality of the vector space. Okay, so now I have taken gamma as another vector, so that is basically beta minus inner product of beta alpha by norm of alpha square into alpha. So, we have, if gamma equal to 0, this implies that beta can be written as a scalar multiple of alpha. This implies beta equal to inner product of beta alpha by norm of alpha square into alpha. This is a scalar quantity. So, beta is basically a scalar product of the alpha place. Now, let me consider beta not equal to, let beta not equal to beta alpha by alpha, I mean beta not equal to simply a scalar multiple of alpha. So, in that case, so gamma not equal to 0 in that case. So, gamma not equal to 0 means, okay, we have inner product of gamma and alpha, let me check that one. Inner product of alpha, gamma and alpha equal to inner product of beta minus beta alpha and alpha. So, this is equal to inner product of beta alpha minus inner product of beta alpha by alpha square into inner product of alpha alpha. So, I have used basically the property of the definition of the inner product. From that I can write down that inner product of gamma alpha like this. So, this is equal to, you see, inner product of beta alpha minus inner product of beta alpha only. So, this is equal to 0. So, this implies that we have considered a vector gamma such the inner product of gamma and alpha equal to 0. We have 0 is strictly less than gamma and gamma, inner product of gamma gamma, because if I have considered gamma not equal to 0. So, gamma not equal to 0. So, this means that inner product of gamma gamma is strictly greater than 0. I mean this will be equal to inner product of your gamma and I can write on beta minus inner product of beta alpha by norm of alpha square into alpha. So, 0 less than inner product of gamma and gamma, which is equal to inner product of gamma beta and minus inner product of beta alpha by norm of alpha square and gamma and alpha please. So, we have inner product of gamma gamma, that is equal to this quantity, but this is equal to 0, already we have seen it. So, this is equal to 0. So, this implies that 0 is strictly less than norm of gamma square, which is equal to inner product of gamma and beta, please. And this is equal to, again, according to the definition of the gamma, this is equal to beta minus inner product of beta alpha by alpha square and alpha, and then beta, please. So, this is equal to inner product of beta beta and minus inner product of beta alpha, take it out, by of course by norm of alpha square. Then I am getting here simply alpha beta, please. So, this is equal to norm of beta square minus absolute value of inner product of alpha and beta, this whole square, please, and divided by norm of alpha square. So, this implies that 0 less than norm of beta square into norm of alpha square minus inner product of alpha beta whole square. So, here I have taken this strictly less than 0 is strictly less than this quantity based on gamma not equal to 0, please, gamma not equal to 0 and gamma not beta not equal to, again, linear scalar multiple of alpha, please. Okay. So, if you do not consider that one, then it will be less than equal to also, please. So, this implies that I will have mod of inner product of alpha beta whole square is less than norm of beta square and norm of alpha square, please. This implies mod of inner product of alpha beta will be less than norm of beta into norm of alpha, please. Anyhow, so equality will come into the picture if you consider that beta equal to inner product of beta alpha by alpha square into alpha, please, I mean scalar multiple of alpha. So, in that case equality will come to the picture, please. Okay. The next result was that triangular inequality. We have to show that norm of alpha plus beta is less than or equal to norm of alpha plus norm of beta. So, for this we have see norm of alpha plus beta whole square, that is equal to norm of alpha square plus norm of beta square, already we have proved it, plus 2 times real part of inner product of alpha beta, please. This already have established this result, please. So, this implies norm of alpha plus beta whole square will be less than or equal to norm of alpha square plus norm of beta square plus 2 times of real part, I will say, okay, absolute value of the inner product of alpha beta, please. So, I can say real will be vanish because we have taken the absolute one. So, I will say that 2 times of inner product of alpha beta, please, absolute value of the inner product of alpha beta, please. So, this implies that this is less than equal to norm of alpha square plus norm of beta square plus 2 times by Cauchy-Schwarz inequality, that is from 3 already have proved, we will have this is less than equal to norm of alpha into norm of beta. So, this is equal to norm of alpha plus norm of beta whole square. So, this implies norm of alpha plus beta is less than or equal to norm of alpha plus norm of beta. This is triangular inequality please. So, you will see the application of 3 and 4 is rigorous. In many places we use Cauchy-Schwarz inequality, we also use the concept of triangular inequality please. Now, let me consider some example please. Let V is equal to, let me consider V may be say Fn, space of n tuples. Here this field is real number or complex number please. Let inner product is standard inner product on Fn. So, let alpha which is equal to x1, x2, xn and beta equal to y1, y2, yn be any two elements of V equal to Fn. Then inner product of alpha beta, then we have inner product of alpha beta equal to sigma xj yj bar, j equal to 1 to n please. So, this implies mod of inner product of alpha beta is equal to sigma j equal to 1 to n xj yj bar, this quantity please. Okay. So, according to the Cauchy-Schwarz inequality, summation j equal to 1 to n xj yj bar, this quantity will be less than equal to inner product of alpha and inner product of beta. Inner product of alpha is equal to j equal to 1 to n xj into xj bar, that is xj square, that is I can say mod of x square, this whole power 1 by 2, inner product of alpha alpha square root, positive square root, that one, into again mod of yj square j equal to 1 to n, this whole power 1 by 2 please. Now, this is over our Fn. Now, you have, let me consider another examples, that is space of say continuous function say. Let V be the space of real or complex valued continuous function on the closed interval 0 1, and let the inner product in V be defined by for any f and g belongs to V, inner product of f and g, let me write down, this is equal to your 0 to 1 f of x and g of x bar dx. So, this is the inner product of f and g and the two elements of this one place. Now, according to this Cauchy-Schwarz inequality, so using Cauchy-Schwarz inequality, CS inequality, Cauchy-Schwarz inequality, we have integration from 0 to 1 fx gx dx, this is less than equal to I will say that absolute value is less than or equal to inner product of f and f. So, that is equal to 0 to 1 mod of f of x whole square dx whole power 1 by 2, and again integration of 0 to 1 mod of gx whole square dx power 1 by 2. So, we will discuss more problems in my next classes. So, I hope the concept of this inner product space and some properties in inner product space is clear. Now, let me introduce one more terminology, interesting terminology called orthogonal vectors, please. Orthogonal vectors. Let V be an inner product space, let alpha and beta be any two vectors in V. Beta is said to be orthogonal to alpha provided inner product of alpha beta equal to 0. So, beta will be orthogonal to alpha provided inner product of alpha beta equal to 0. If inner product of alpha beta equal to 0, then inner product of beta alpha equal to also 0. So, this implies alpha is also orthogonal to beta, please, orthogonal to beta, please. For example, let me consider let V is equal to my R2 space, and let me consider the standard inner product on E as a, this is a standard inner product, standard inner product. Okay. So, let alpha equal to x comma y. So, we want to know an element beta in V which will be orthogonal to alpha. So, immediately I can see that then beta which is equal to minus y x or y minus x will be orthogonal to alpha. Since inner product of alpha beta is equal to x into minus y plus y into x which is equal to 0. If I consider over the same space, let me change the inner product. Let inner product is given by like this, that let me consider, say, let alpha equal to x1 x2 and beta is equal to, say, y1 y2, and let me define inner product as inner product alpha beta equal to x1 y1 minus x2 y1 minus x1 y2 plus 4 x1 x2. Already we have seen this introduce an inner product over the R2. Now, if alpha is equal to, let me consider x y and beta is equal to, say, minus y x is orthogonal to alpha, then we will definitely have inner product of alpha and beta will be equal to 0. But in this case what I am getting here, if I consider that as in the case of the previous one what the standard inner product space, that for alpha equal to x comma y, beta equal to minus y comma s is orthogonal. Now here beta equal to minus y comma x will be orthogonal provided, let me see what are the conditions. See, this is equal to 0 means x into minus y minus x2, that is y into y1 means minus y, then minus x1, that is x into and y2 means x, and plus 4 x1, that is x, and x2 means again x. This is 4 x2 y2, x2 y2. So this means that y2 equal to x. So this is equal to 0. So this means that I am getting y square minus x square plus 3yx equal to 0. So from this I will have a relation between y and x, for which that alpha and beta will be alpha will be orthogonal to beta or beta will be orthogonal to alpha, please. So one can have immediately here y will be equal to minus 3 x plus minus root over 9 x square and 9 x square b square minus 4 ac, that is 4 into x square, right, that is plus by 2. Okay, some sort of this relation will get it, please. So something like minus 3x plus minus root over 13 x by 2. So y will definitely related by x in this way, please. Again we can see over the space of say continuous function, another, let me take another examples. Let V be the space of all real valued continuous function in closed interval say minus pi to plus pi. Then sin t is orthogonal to cos t. So this you can check it as a homework, please. So we will discuss more about this orthogonal sets and orthogonal vectors in our next class, please. So we see that the two vectors they will, if they are orthogonal, they have to satisfy certain criteria, and then again we have seen that over the space of real continuous function in the closed interval minus pi and plus pi, the function sin t is orthogonal to cos t or cos t is orthogonal to sin t, please. So we will discuss more on this orthogonal sets in and some properties of this in our next class, please.